Visualize for a moment. The time isn't just a straight line stretching endlessly from past to future. Picture instead the familiar tick-tock of a clock. But now that clock begins to melt and twist, much like a surreal painting by Salvador Dali. As the hands dissolve, the image zooms out to reveal something even stranger, a shimmering cube, its edges pulsing with energy, and along each axis, time itself unfolds, not in one direction, but in three. What if, all this time, we've been confined to a single thread of time, blind to the vast landscape of temporal possibilities that surround us? This isn't a scene from science fiction. In April 2025, a geophysicist named Dr. Gunther Kletetschka, an associate professor at the Geophysical Institute of the University of Alaska Fairbanks, and also affiliated with Charles University, proposed a bold new theory that could upend our entire understanding of reality. Published in the Reports in Advances of Physical Sciences, his work suggests that, just as our universe has three dimensions of space, it also has three independent dimensions of time. This daring idea doesn't just tweak the equations of physics, it rewrites the very fabric from which space itself is woven. Why propose something so radical? The answer lies at the heart of the two greatest achievements of modern physics, general relativity and quantum mechanics. These two frameworks have each explained enormous swaths of the cosmos, from the dance of galaxies to the flicker of subatomic particles. Yet, for over a century, they have refused to fit together. Gravity, as Einstein described, is the curvature of space-time itself, a smooth and continuous surface. Meanwhile, the quantum world is jittery, probabilistic, and fundamentally uncertain. Physicists have tried for decades to find a unifying theory, something that can reconcile the smooth with the granular, the cosmic with the quantum. Kletetschka believes the missing piece is our understanding of time. In his theory, time is not just a passive backdrop, a silent observer as events unfold. Instead, it is the most fundamental substance of reality, the fertile ground from which everything else, including space and matter, emerges. Imagine a three-dimensional grid, but instead of measuring left-right, up-down, and forward-backward, each axis measures a different aspect of time. The first dimension is the one we experience every day, the relentless forward march from yesterday through today towards tomorrow. This is the familiar flow of time, the arrow that gives us cause and effect, memory and anticipation. But the second dimension of time is something stranger. Rather than representing progression, it describes the alternatives, the branching paths of possibility that exist within a single moment. Every instant, according to this theory, contains a vast landscape of what-ifs, different realities that could unfold based on the tiniest fluctuations or choices. It's a bit like the many worlds interpretation of quantum mechanics, but with a crucial twist. These alternatives are not separate universes, but coordinates within an expanded temporal space. The third dimension is the bridge, the connective tissue that allows for transitions between these possibilities. It's not just about choosing a path, but about the rules that govern how and if one can navigate from one temporal possibility to another. This three-dimensional structure of time doesn't explode causality or allow for paradoxes. The infamous grandfather conundrum remains safely impossible. Instead, it preserves the logical structure of cause and effect, but within a much richer, more intricate tapestry. How does this three-dimensional time differ from other bold ideas in physics? The multiverse theory, for example, suggests infinite parallel universes, each with a different history, but it doesn't provide a mechanism for how or why these universes exist, nor any way to interact with them. The loop time hypothesis plays with circular or repetitive time, but often at the cost of logical consistency. Kletetschka's approach is more conservative in one sense. It keeps the mathematics grounded. His model uses a unique signature, written as plast, to describe how the three temporal dimensions and three spatial dimensions interact. This signature is carefully chosen to keep the equations stable and prevent runaway solutions that would make reality itself impossible. While reminiscent of 2T physics, advanced by Itzhak bars, which posits two time dimensions, this new theory is more ambitious, proposing a full three. But perhaps the most exciting aspect of Kletetschka's theory is that it makes real, testable predictions. It claims to calculate the masses of fundamental particles like electrons, muons, and quarks, quantities that, in the standard model, are simply plugged in by hand. Even more provocatively, it predicts that two specific resonances, signatures of new particles or phenomena, should appear at around 2.3 trillion electron volts, TeV, and 4.1 TeV in the data from the Large Hadron Collider, the world's most powerful particle smasher. The theory also forecasts a minuscule but exact deviation in the speed of gravitational waves, the ripples in space-time caused by cataclysmic cosmic events. According to Kletetschka, the ratio of this change to the speed of light should be about 1.5 times 10 to the minus 15th. These numbers aren't just abstract, they're concrete targets for experiments already underway. So where will this theory face its trial by fire? The Large Hadron Collider, as it embarks on its third run, is hunting for the predicted resonances, peaks in the data that would hint at new physics beyond the standard model. At the same time, the global network of gravitational wave detectors, LIGO in the United States, Virgo in Italy, and Kagra in Japan, are pushing the boundaries of precision, measuring the speed of these waves with astonishing accuracy. Meanwhile, space missions like Euclid and the Vera Rubin Observatory are mapping the cosmos in exquisite detail, searching for the fingerprints of dark energy. If time truly has three dimensions, it should leave a subtle but unmistakable mark on the cosmic fabric, an energy pattern that current models can't explain. But as of now, the evidence remains elusive. The LHC's latest datasets have shown no strong peaks at the predicted energies, no sign, yet, of the new resonances. The velocity of gravitational waves, as measured from events like GW 17.17, matches the speed of light to within the tiniest measurable fraction, a result that Kletetschka's theory can accommodate, but so can many others. The search goes on, but definitive confirmation has not yet arrived. This brings us to the crucial question: how is this theory being received? While it offers an elegant new perspective, Kletetschka himself is not part of the mainstream community working on particle physics or gravity. His proposal, while mathematically sound, needs rigorous independent review and experimental validation. There's also a danger of post-adjustment, tuning the theory to fit masses that are already known, rather than making bold predictions that could be falsified. As with any dramatic departure from established models, skepticism is high. Physicists demand not just clever mathematics, but hard evidence, data that only the universe itself can provide. Yet, the stakes could not be higher. If time truly has three dimensions, the implications are staggering. The universe would be far stranger and perhaps more navigable than we have ever imagined. Instead of being carried helplessly along a single current, reality might allow for a richer form of existence, one in which we could, in principle, explore the branching rivers and hidden channels of time itself. The answer to one of science's oldest mysteries might not be light years away, but hidden in the trillions of electron volts unleashed at the LHC, or in the faint tremors of space-time captured by our most sensitive detectors. So, what do you think? Are we on the verge of a revolution in our understanding of reality, or is this another beautiful idea destined to fade? If you enjoyed this journey to the edge of science, be sure to subscribe to The Curious Order and join us as we continue to explore the wildest frontiers of the universe. The next great discovery could be just a moment or a dimension away.